On this episode of Assignment Discovery, travel from Japan to San Francisco and marvel at the masterpieces of structural engineering in bridges, design, and function. Get behind the scenes to look at the most dramatic successes and failures in the history of bridge building. Finally, watch what can happen to these elevated structures when natural disaster strikes. And for lesson plans on structures, go online to discoveryschool.com. Consider this before viewing Bridges, Design and Function, Part 1. How has bridge design evolved through the centuries? What innovations have enabled these changes to happen? As you watch, list the 4 types of modern bridges discussed in the program. Note how the location and the type of bridge determine the materials used to build it. Watch how engineers try to control wind, water, and weight to keep these structures standing. Assignment Discovery now presents Bridges, Design and Function, Part 1.
They come in all shapes and sizes. Some are made of concrete. Some are made of steel. The best are heart-stopping symbols of human achievement. The worst remind us that great ambition can lead to great failure. The challenges are many, but the rewards are vast for the men and women who build bridges. Bridges are the superstars of engineering. We may admire skyscrapers for their grandeur, and we can respect the sheer effort it takes to build a tunnel. But bridges are loved. Unlike many other human creations, a great bridge can enhance the beauty of its setting. But for all their glamour, the first duty of a bridge is to fulfill its function, providing safe crossings over impassable terrain. Many road bridges hide their structures underneath, so the average driver surveys nothing but pavement. These bridges can be every bit as challenging to build as their king-size cousins. David Goodyear is building such a span. As the designer and chief engineer of the new Crooked River Bridge, Goodyear is using state-of-the-art methods to build an $18 million classical concrete arch in Oregon's high desert. It's a difficult task because the bridge will cross a 300-foot deep gorge over white water.
The physical challenge of crossing the gorge is quite an undertaking, and as you can see, it's a pretty dramatic sight. It's not the easiest traverse to make, and certainly unlike more of an urban or even a river setting where you're close to terra firma and you really don't have the heights to work with here. There are few alternatives in getting across a gorge like this. Really, for the type of bridge we're building, the concrete arch bridge, there are no choices other than what we're doing beyond going to the valley floor and building falsework up from the bottom, which is, in today's world, prohibitively expensive and too environmentally intrusive.
Arch bridges have been built throughout the world for centuries. They can carry heavy loads, but they're best used over short distances. Engineers found a way to cross longer spaces by turning the arch upside down. In suspension bridges, steel cables hang down in a natural arch from 2 towers. These cables run continuously from an anchorage on one side of the bridge, across the tops of the towers, and over to a matching anchorage. steel ropes dangling from the main cables support the bridge's deck. Cable-stayed bridges are a recent variation on the suspension form. Instead of locking main cables to outlying anchorages, workers use the tower itself as an anchor and extend the deck piece by piece, tethering each section to cables fixed to the tower. Workers on the Crooked River are using cable-stayed methods to construct the bridge's main arch. When the 535-foot-long arch is complete, the towers will be demolished, and a road deck will be added to the top. The latest technology will spawn one of the oldest forms of crossings. Cable stay technology is common in Europe and Japan, but in the United States, it's still new to most construction workers. Bridge builders have learned the hard way that when new methods are employed, it's wise to proceed cautiously.
When you get involved with unique bridges like this, the craft of building it is even more important than with a more routine structure. And really the people whose hands get dirty building the bridge are the craftsmen, the iron workers and the carpenters that are out there. On these types of bridges, especially where you run into complex procedures and complex geometry, we always want to get out and find who the key carpenter foremen and ironworker foremen are, and actually try and make friends and get on good terms with them, because their skill is quite important to a successful project. And quite often they can do their part to keep the engineers out of trouble by seeing things that don't look right and raising questions when things might need to be changed or modified to suit the construction site.
The men and women building the Crooked River Bridge work in a device called the Traveler. The Traveler is a form mold suspended from the edge of the span. To create a new segment, the Traveler is filled with steel and concrete. When the concrete hardens, the Traveler is tugged free and moves up 27 feet. Then the process begins again. Each segment is bonded to the last. There are actually 3 Travelers, 2 that set the beams on the right and left sides, and 1 that follows behind, setting the middle slab.
Okay, Rick, bring her up slow.
Workers move them up with a combination of muscle and a crane fixed to the other side of the chasm. The crane has just enough capacity to lift the 25-ton Travelers. A crew of just 16 men and women is building the new bridge, roughly the same number it took to build the bridge it's replacing. There are 2 other Crooked River bridges nearby. The first is a heavy steel railroad bridge built in 1911. To erect it, laborers had to camp for months down in the gorge near the water supply. Each day they climbed up 300-foot rope ladders to get to the construction site. Conditions were a bit less extreme by 1926, when a 2-lane road bridge was built next to the 1911 bridge. But the construction methods were the same. Both bridges were built by cantilevering sections out and riveting them together.
The other bridges, of course, they were masterpieces of their time when you consider in 1925, 26, people building a bridge over this gorge with the kind of equipment they had. It's quite an impressive undertaking. One of the things about civil and structural engineering is you can go back a long ways with the same comparison back to the time of the pyramids and consider all of the great civil engineering works, and it really puts what we do today in perspective. I think this bridge is supposed to contrast with the other structures, and it will. It'll be beautiful in its own right, really befitting of the glamorous and dramatic setting.
At this point, 1.5 years of construction lies ahead. Workers will extend the north side arch halfway across the gorge, and then they'll pick up and move to the south side and begin the whole process again. Eventually, there will be one more bridge in the world, another quiet marvel of ingenuity nestled in the wrinkles of the earth. This is the Chesapeake Bay Bridge Tunnel. It stretches 18 miles across the waters of the state of Virginia on America's east coast. Opened in 1964, this complex took 3.5 years and $200 million to build. In 1965, an international panel declared the bridge tunnel one of the 7 engineering wonders of the world. But the original bridge can no longer support the increasing numbers of cars and trucks that speed across it every day. Since it opened, there have been 43 fatal accidents here. Many of them were head-on collisions. So in 1995, work began on a parallel crossing that will separate the traffic and double the bridge's size. 18 miles is far too long for a suspension bridge. This location demands a low-lying trestle. But using steel in the midst of the corrosive salt and spray of the Atlantic Ocean isn't an option. So engineers turn to the other workhorse material of construction, concrete. Concrete is a mixture of sand, gravel, water, and cement. It was invented thousands of years ago by the Romans. Then it was rediscovered by the engineers of the industrial age. Together with steel, it is one of the building blocks of the modern world. Designers like concrete because it's cheap and it can be molded into a variety of shapes. But concrete has its failings. Unlike steel, it isn't very elastic. Instead of bending, it cracks. So to strengthen the concrete, workers pour it into molds filled with steel cables. The cables are stretched to 80% of their breaking point. This locks in tension. The process is called pre-stressing. It's being used to create the super strong slabs that will form the bridge's roadway. The new bridge will consume close to 275,000 cubic yards of concrete. That's a block as long as a football field, standing 16 stories high. After deck segments have been poured, they're covered in plastic and allowed to cure overnight. To accelerate the hardening, steam heaters bake the segments at about 150 degrees Fahrenheit. Then the segments are hauled off to the docks to await their trip out to sea. Each segment is 100 feet long and weighs 140 tons. All of this pouring, lifting, and hauling only gets the prefabricated concrete to the barges. It's when these pieces are out at sea that the really big machine goes to work. The IB-909 is one of the largest construction devices in the world. Like an oil rig, it extends legs down to the sea floor, providing a stable platform for its floating cranes and pile driver. Although the scale of construction is oversized, building this trestle bridge is relatively simple. First, hollow piles are hoisted into position. They range from 70 to 185 feet long. They weigh about 1,000 pounds per foot. The piles are driven into the bottom of the sea by a gigantic air hammer. Each pile can stand up to 250 tons of pressure, so cracking is rare, even under the repeated force of these blows. Next, 48-ton caps are hoisted over and lowered into their permanent homes. The piles and caps are treated with ground-up blast furnace slag that makes them impermeable to water. Calcium nitrate is also added to neutralize salt from the ocean, which could rust out the concrete steel reinforcements. Finally, sections of roadway deck are laid 3 across the pile caps. This process will be repeated over and over for 3 years until 1,895 segments have been hoisted into place. After the IB-909 crew has done its work, an army of men and women move onto the road deck, turning its rough superstructure into a tight, finished product. Altogether, more than 600 people work on some part of this bridge, day and night. It's not always easy. A little more cement seals the cracks. Then it's time to clean up the road and insert the guardrails. The last things added are the asphalt road surface, and of course, double yellow dividing lines. The new bridge will cost $198 million. When it's finished, traveling this route will be easier and safer. But bridge lovers probably won't give the Chesapeake Bay Bridge Tunnel the acclaim they grant the steel titans of the past. The history of giant bridge building is filled with grand successes and spectacular failures. Engineers are forever trying to push back the barriers of bridge design without sacrificing safety and economy. New York's Brooklyn Bridge is a prime example. It was designed by John Roebling, a man obsessed with the way structures respond to the forces of nature. Finished in 1883, this bridge incorporated all of his ideas about controlling wind sway through the inventive and often beautiful use of masonry and steel. The deep, stiff truss supporting the road deck was a central part of his concept. Another was his unique use of vertical and diagonal steel cables to help the deck resist the tug of the wind. These innovations allowed Roebling to safely reach out 1,595 feet, making the Brooklyn Bridge the world's longest suspension span. But despite his success before the 20th century, suspension bridges were viewed with suspicion. Many felt they were too fragile to withstand bad weather. The public put its trust in giant cantilevered truss designs, such as Scotland's Forth Rail Bridge. Built in 1890 and extending 1,710 feet, this was the first large-span bridge built entirely of steel. It was designed to be nearly indestructible. 10 years before, a nearby bridge had toppled over in a heavy gale, so the Forth Rail's engineers deliberately built the biggest, heaviest, and strongest structure possible at the time. It cost a fortune, but the rock-solid design inspired confidence. Engineers and elected officials the world over became convinced that cantilevered truss bridges were the ideal forms for long crossings. All that changed in 1907 during the construction of the Quebec Bridge. At 1,800 feet, this was to be the world's longest cantilevered span. But during construction, a giant steel arm buckled and fell, killing 75 men and bringing down the entire structure. Blame was placed on the chief engineer, who was not on site to make sure the bridge was being built according to specifications. Although it was eventually rebuilt, its initial failure left a lasting mark on engineers and the public. After the Quebec Bridge disaster, the designers of cantilever truss bridges fell out of favor. A new breed of bridge builders rose to power. They championed streamlined suspension bridges built out of high-strength steel. Manhattan's George Washington Bridge was their first great success. Its towers were tall and daringly unadorned by masonry shells. Its roadways were long, slim, and sleek. Everything about it proclaimed that a new age of bridge design had been born. Confidence in the design ran from its builders down to the soldiers who marched across the bridge on opening day in 1931. The men marched in cadence, breaking a common rule not to lock step on a suspension bridge for fear of setting into motion a resonant vibration that could bring the bridge down. The bridge didn't fall, but it did quiver. It also quivered in high winds, for as the roadways of modern bridges grew thinner, they also grew more flexible, not only under traffic, but also against the wind. Engineers knew there was a limit to how skinny a bridge deck could get before it fell apart. But they were certain they could avoid any problems. Deck sway was less of an issue with the bridge that stole the world's records for height and length in 1937, San Francisco's Golden Gate. Its road deck was thin, but it was also quite wide, which helped to keep it stable. Driven on by their triumphs, engineers pushed harder at the barriers of bridge design. And then one day, the barriers pushed back. It happened in a remote corner of Washington State in 1940. The Tacoma Narrows Bridge was the third longest suspension span in the world, and the most daringly designed. Here the streamlined shape was taken to its limit. The deck was only 2 lanes wide and remarkably thin, a feat accomplished by building the roadway on a solid steel girder rather than an open truss. Open truss decks allow wind to flow through a bridge rather than bounce against it. The Tacoma Narrows solid deck made it behave like an airplane wing. In even moderate winds, it lifted. Locals nicknamed it Galloping Gertie. Engineers came out to study its movements. They learned a powerful lesson when the bridge's oscillation in a light wind turned into a fatal vibration that ripped the deck apart. Confident in their designs and the prevailing engineering theories of the day, the bridge's planners had simply not imagined that the wind could have such a destructive effect on their state-of-the-art span. The disaster forced bridge builders to follow a cautious path for the rest of the 20th century. Thin girder road decks were abandoned in favor of thick, open trusses.
Now that you've seen Bridges, Design and Function Part 1, talk about this. The program describes the design features of 4 different types of bridges. Think about some bridges in your area and discuss how their structures resemble the bridges from the program. Why do you think the engineers included these structural features in their designs? Now try this. Using household products, build a scale model of one of the 4 types of bridge designs. Explain the structure and function of your model to the class. Log on to discoveryschool.com for curriculum materials and resources to support Bridges, Design and Function. To learn more, Assignment Discovery suggests Bridgescape by Frederick Gottmuller. Consider this before viewing Bridges, Design and Function, Part 2. What factors would you need to consider if you set out to design the longest suspension bridge in the world? Think about how environmental factors would affect your design. While you watch, see how Japanese engineers approach these issues in the design and construction of the Akashi Kaikyo Bridge. Assignment Discovery now presents Bridges, Design and Function, Part 2.
Today, wind tunnel testing has become an important part of engineering design. By blasting scale models with high-speed winds, engineers can get a close approximation of how bridges and buildings will behave in the real world. But close doesn't mean perfect.
Engineers are expected to be infallible, but they're of course not, just as no one else is infallible. We have generally accepted codes and standards to live by, but again, they take care of the more routine and the expected events rather than the unexpected, and it's the unexpected that always jump up to bite you. It doesn't always happen that just going into a wind tunnel gives you all the answers. There are a lot of unknowns, and there probably always will be a lot of unknowns, but you try and minimize the risk from them.
The shrines of Japan are deceptively simple designs that harmonize with their environment. These buildings are simple and elegant, built for endurance, not for flash. Japanese bridge design follows a similar path. Bridges here are often thicker and heavier than their cousins in Europe and the United States. The engineering is state-of-the-art, but cautious. Nothing gets built without first undergoing extensive laboratory testing. For despite their skill and their passion to break records, Japan's bridge designers have to cope with the fact that their nation is subject to some of the worst weather on the planet. Violent rainstorms batter the country for months on end, dumping 57 inches of water every year. Typhoons are common, so are earthquakes. Engineers respond to this challenge by designing bridges that break all the records, but never break the rules. The Akashi Kaikyo Bridge is the ultimate expression of their struggle to temper ambition with conservatism. Opened to traffic in 1998, the Akashi is the longest and tallest suspension bridge in the world. It is the product of 20 years of testing and more than 10 years of construction. It came with a price tag of more than $4.5 billion. But that kind of money buys a lot of bridge. The Akashi is 2.5 miles long. Its center span alone is a sprawling 6,532 feet. You could fit 4 Brooklyn bridges inside of it. Its 2 towers are 927 feet tall, beating out the Golden Gate by nearly 200 feet. By any standard, this is an amazing engineering achievement. And it's all the more remarkable when one considers that the bridge was built across a fault line. One side of the bridge rests near Kobe, the 7th largest city in Japan and a busy international port. For years, the only way to make the 6-mile crossing from Kobe to nearby Awaji Island was to take the ferry boat across the Akashi Strait. But in 1955, the storms that continually racked these waters struck hard. 2 ferries sank, killing 168 school children. The public demanded a safer way to make the crossing. A bridge was called for, a bridge like no other. It would have to stretch across the channel and have a center span high enough to let vessels of all sizes pass underneath. At such a size and in such a vulnerable location, the bridge's designers realized that this span would have to undergo an unprecedented series of trials. For more than a decade, they subjected models of the Akashi to brutal tests that simulated the effects of earthquakes and high winds. The winning design was a heavy steel structure that can withstand 180 mile-per-hour typhoons and earthquakes up to magnitude 8.5. The Akashi is a handsome brute of a bridge, a samurai warrior covered in armor and bulging with muscles. Its main cables are thick, and its road deck is wide and stiff, so it is less likely to sway. The truss supporting its road deck is hollow, allowing wind to flow through. Inside, the truss is an enormous cavern of steel girders. Due to the Akashi's size, the wind load these girders sustain is greater than any other bridge in existence. Engineers compensated for this by constructing the platform out of 90,000 tons of steel. This is also the home of the bridge's arteries, pipes that blast hot air through the main cables to keep them from corroding. Construction of the Akashi Kaikyo Bridge began in 1986. First and most difficult, twin caissons had to be embedded in the sea. Each hollow caisson weighed 15,000 tons and stood 230 feet high. Towing them into position took weeks. The caissons were sunk into the bed of the sea and filled with concrete. Then floating cranes assembled the bridge's enormous towers. At 98 stories, the Akashi is nearly as tall as the Eiffel Tower. Sumitaka Kurino is head of engineering maintenance on the now complete Akashi Kaikyo Bridge. Kurino worked on the design and construction of the bridge's 2 towers. As the towers were built, Kurino and his team faced a problem that years of testing had not been able to predict.
The basic style used for this bridge is very classical, one that has been around for a long time. A suspension bridge supported by girders is a classic style. However, many new technologies were used to build this bridge. Existing bridges have towers that swing at the top when they are blown by the wind. But when the main cables are installed over the top, the towers no longer sway. However, this bridge is nearly 1,000 feet tall, an unprecedented height. Therefore, when it is pressed from the top, the middle also sways. We discovered a phenomenon where the middle sways when the top and the bottom are fixed. In order to prevent this from happening, we installed tuned mass dampers.
First used in skyscrapers, tuned mass dampers, or TMDs, are counterweights that correct shaking by swinging in the opposite direction. Each Akashi tower holds 20 TMDs. Acting together, the TMDs can exert 200 tons of corrective force on each 23,000-ton tower. After they installed the TMDs, workers began the next phase of construction, stringing the bridge's main cables. One at a time, wire strands were connected to an automated carrier and pulled across the Akashi Strait. They eventually pulled more than 186,000 miles of wire, enough to circle the Earth 7.5 times. The ends of the strands were locked inside anchorages on both sides of the strait. Anchorages are mammoth concrete blocks that absorb the bridge's downward force. Each block weighs 350,000 tons. Visitors seldom enter these enormous caverns. Here, the 290 bundled steel strands that form the main cables splay out into fine webs of high-strength wire, developed specifically for this span. The wires are the key components of the bridge. They bear the 112,000-ton weight of the road deck. Kept under constant tension, the wire ends are locked into a solid steel frame embedded in concrete. By January 1995, the main cables had been set. Workers were ready to begin the last phase of the erection, putting the bridge deck into place. But nature intervened. Before dawn on January 17th, an earthquake measuring 7.2 on the Richter scale struck the Akashi Strait, decimating the city of Kobe. Hundreds of thousands of buildings were destroyed, along with bridges and viaducts that were supposedly earthquake resistant. For the builders of the Akashi Kaikyo, the disaster was the ultimate design test. The epicenter of the quake was only 6 miles from the construction site. Fortunately, the quake had little effect on the bridge, but the shifting of the earth widened the distance between its towers by 3 feet. Work resumed a month after the earthquake. The wire ropes that suspend the rope deck were hung from the main cables. Then the deck itself was assembled. It was built out of 1,800-ton girder blocks attached to the towers by a giant floating crane. Finally, after 12 years of construction, the Akashi Kaikyo Bridge opened in April 1998. The Akashi Kaikyo is not only the world's longest bridge, it's also the most expensive. Estimates on the actual cost, including research and testing, range from $4 to $9 billion. Part of the cost is passed on to commuters, who pay a $27 toll each way. For their money, they're rewarded with a bridge whose safety and strength has been virtually guaranteed by its cautious builders. The high cost and the sheer difficulty of undertaking such an enormous project guarantees that the Akashi Kaikyo will remain the world's longest bridge for decades to come. Over time, the economics will be forgotten, but the bridge's blend of strength and beauty will remain. The Golden Gate Bridge opened May 28, 1937. Today it is probably the world's most famous span. For years it held the record for height and length. Now it is an icon, a piece of history that still plays a vital part in the lives of the 118,000 commuters who drive across it every day. As times have changed, so has the bridge. Over the years, its steel suspending ropes have been replaced, and its concrete road deck has been swapped out for a stronger composite material. Engineers have tried to help the bridge endure the ravages of time and disaster. In 1989, the Loma Prieta earthquake rocked the San Francisco Bay Area with a force measuring 7.1 on the Richter scale. Damage was widespread. The San Francisco-Oakland Bay Bridge partially collapsed. But the nearby Golden Gate emerged without a scratch. Experts credited the bridge's sturdy construction, but they also concluded that a bigger quake could have destroyed the bridge and left San Francisco cut off from the mainland. So now bridge managers have launched a 10-year, $217 million effort to toughen up the span. Steel is being reinforced. Motion dampers will be added in key positions. When the work is done, the bridge should be able to withstand an earthquake of magnitude 8.3. Day-to-day maintenance is just as important. The Golden Gate has a full-time staff of 18 iron workers and 40 painters. Their job is to protect the steel. The iron workers are gradually replacing the bridge's 4 million original rivets with high-strength steel bolts. Up above, veteran bridge workers Bill Owens and John McEllistrom walk the Golden Gate's 12,250-ton main cables, looking for signs of deterioration. If necessary, they'll battle the elements in a 746-foot drop to apply a coat of the bridge's famous vermilion paint.
You have 4 different crews, so overall it takes about 10 years and about, let's say, 10,000 gallons of paint to do it all from end to end. It isn't all painting, you know, you have to blast and chip it and prepare the steel. If it was only just paint, that wouldn't be anything.
Paint protects the Golden Gate from the salt air, which could corrode its 83,000 tons of steel. Decaying paint is sandblasted off, then replaced with a gray primer. The orange top coat goes on last. McEllistrom has been doing this for 25 years, long before eye protection and safety harnesses were standard equipment.
Well, they didn't have a safety equipment like they do now. My opinion is that it's great to have it, but you shouldn't be working here if you can't work without it. You have to have confidence in your partner that he will save you. It's no good having a partner that's scared because you know, well, he'll say, I'm going, you're on your own. So you shouldn't be out here if you need it.
But you should have it at all.
You should
You should be wearing it, and it should be along with you. And just because there's always the unexpected things that can happen.
Keeping the unexpected from happening to commuters is the ultimate point of this constant maintenance. San Franciscans love the Golden Gate, but they don't always love the drive.
The best thing about the bridge is the fact that it's there. And people from Marin County can get to the city, and people from the city to Marin County. That's the best thing about the bridge. The worst thing about it is there are too many of us trying to cross that bridge at one time. The traffic gets to be pretty bad. And of course, one little wrong happening in the traffic, a fender bender, some guy running out of gas, whatever it might be, causes a tremendous backup. Just too many of us trying to cross that bridge.
Retired radio personality Frank Dill has lived in the San Francisco area for 40 years. His is one of the 41 million cars that will cross the Golden Gate this year. Like every other commuter, Dill pays the toll for the privilege.
I'll give him a 20. Make him work for the $3. How about that?
You're a real Highlander.
The Golden Gate's talkative toll takers are almost as famous as the bridge.
I gave you a 20 there.
Everybody knows me. In fact, I've been here 25 years, and I know 4 generations of people, their grandparents, the parents, their children, and their children's children. This is like working for a public monument, and tourists come out here to see us. It's like working for the Grand Canyon or Yosemite. And they ask questions, and you have a lot of people from all over the country or all over the world, and you like to kid them, and you like to speak in their languages. How you doing? Where are we going today? Any place exciting? Japan. Japan?
Toll takers collect nearly $5 million a month. The revenue pays the salaries of the 180 people on the Golden Gate staff.
Go ahead, Unit
That
6-2.
staff includes a large security force. Its members are on a round-the-clock lookout for accidents, crimes, and misdemeanors. Stalled cars and fender benders are common, but now and then a bit of San Francisco surrealism creeps in.
Responded at southbound Doyle, 1125.
God, anything that happens anywhere happens out here. We've had strange events like babies being born in a toll plaza. Lisa actually helped deliver one baby not that many years ago. Anything that happens anywhere happens out here. It's just like a little city.
Will, did you hear about that?
Golden Gate workers are a family, literally in the case of Mike and Lisa Licati. They were married after spending hundreds of hours working together at one of the most romantic spots in the world. The vast scale of the Golden Gate, like many other large bridges around the world, can make humans feel very small. But great bridges are also a legacy that one generation leaves for those to come. With proper design, maintenance, and a little luck, they will stand for centuries. Steel and concrete proof that beauty and functionality can walk hand in hand.
Keep watching. Discussion topics and activity and resources for bridges, design, and function are up next on Assignment Discovery. Now that you've seen Bridges, Design and Function Part 2, talk about this. Bridge engineers are not infallible, and errors in their calculations can cost lives. Discuss the steps that engineers take to minimize the risk of design failure. Be sure to explain how these precautions differ depending on the location and the type of bridge. Now try this. Write a proposal for the construction of a new bridge in the location of your choice. Describe why the bridge is necessary and what type of structural features would be most suitable. Be sure to use engineering facts to support your proposal. Log on to discoveryschool.com for curriculum materials and resources to support Bridges, Design and Function. To learn more, Assignment Discovery suggests Bridges by Stephen A. Ostro.